Hi, this is Kenneth Wong, Senior Editor for DE. In the upcoming CAASE21 online conference, Karen Wilcox will be delivering a talk on digital twins, its subtitle, From Physics-Based Modeling to Scientific Machine Learning. So today, I want to spend a few minutes exploring the topic of digital twins. Karen, welcome. Can you say a few words about who you are and what you do?
Sure. It's nice to be here today talking to you, Kenneth. I'm a professor of aerospace engineering and engineering mechanics at the University of Texas at Austin. And there at UT Austin, I also direct the Odin Institute for Computational Engineering and Sciences, which is a large institute that's really focused on advancing computing for challenging applications across science, engineering, and medicine. So we're a very broad institute that really touches many corners of campus.
Since your talk is about digital twins, I want to ask you if there are certain industries that seem to be more mature or better positioned to take advantage of the digital twins and better at implementing. And are there something about these industries that make them so?
Well, digital twins have their roots in aerospace engineering, Kenneth, and in fact, even though the term is more recent, the term was coined about a decade ago, the idea is much older, and many people actually point to the Apollo program as being a place where digital twins were first put into practice, where NASA would keep digital simulators on the ground to follow along with the spacecraft that were actually launched up into space. And so I think we could certainly point to aerospace engineering as being one of the industries that really is at the forefront of using digital twins. And you ask, what is it that leads to it? I think some of it is that history, the fact that aerospace engineering traditionally has been at the forefront of using modeling and simulation and using advanced computing to drive decision making. And so with the increase in data and then the improvements in algorithms to analyze that data at scale and to combine it with models, it's kind of a natural confluence for many of the applications in aerospace engineering to take that and manifest it as digital twins. But the compelling examples are well beyond aerospace, and we see a lot of, I think, really exciting examples, for example, in civil engineering and architecture and urban infrastructure, with things like energy efficient buildings and predictive maintenance on bridges. We've seen digital twins with wind turbine farms, hugely complex offshore platforms. So all the places where you would really like to know what's going on at with your system at the individual level, but perhaps human-driven or manual maintenance is expensive or awkward. Those are the places where I think the most compelling uses of digital twins are happening today.
One aspect of your talk is machine learning or the AI applications. I wonder if you can help us understand its relevance to digital twin maintenance and improvements.
Machine learning clearly has a big role to play because it brings powerful algorithms and powerful ways of framing the problem of learning from data. But I do want to emphasize that machine learning is just one piece of the problem, that when it comes to building a digital twin of something like an aircraft, which is the work that I'll talk about, just simply trying to learn from data with black box machine learning methods is never going to get us there, because we also need that predictive modeling aspect that is going to let us reason about and make predictions for our system to guide critical decisions. So the work that we're doing really is an integration of, again, powerful machine learning that lets us deal with data at a large scale and learn from that data through the lens of predictive physics-based models. And we put all that together in what is known as a probabilistic graphical model, and putting it in that framework brings another really important point, which is the need to quantify uncertainties.
One follow-up question, if I may. Our readers are very familiar with finite element analysis programs, of course. They seem to be typically targeting solving one scenario at a time. You have this geometry, and these are the loads, and these are the stress loads, and these are the safety factors that you want. So what is the best repositioning of this geometry to deal with this? But if you have machine learning and you have a large data set, you have, say, a week's worth of turbine wind conditions in turbine. Are the FEA programs right now actually able to take advantage of that kind of data?
Absolutely, that's a great question, Kenneth. So thinking about moving something like finite element analysis from just the single one or two analysis cases to really being a powerful prediction tool that crosses a range of scenarios. And like you say, we might have weeks worth of data covering many different scenarios. And at the same time, we're going to need to make predictions for the coming week where we might expect to see, again, many, many different scenarios. So that's where you really get into the realm of parameterized models. And of course, the finite element method is a sort of beautiful predictive physics-based platform on which to do that. And there's been a lot of work in the past decades in creating those capabilities. Now, it turns out in the digital twin setting, we're typically not going to be able to afford to run thousands and thousands of finite element analyses, especially if we're trying to do updating of the digital twin or predictions in real time. And so a key technology that we use is reduced order modeling or surrogate models, where we really try to create approximate models that embed the power of those finite element simulations, but do it in a way that can be executed very rapidly. And again, that idea of a reduced order model is something that really sits halfway between machine learning and how we learn essential structure and problems, and physics-based modeling, where we really incorporate the structure of the problem.
We know, of course, there is no such thing as a digital twin SDK or a digital twin starter kit. But if we were to imagine something like this for a firm or a company that wants to, for the very first time, launch a digital twin of their physical product counterpart in the field, what are the basic components that they require? Software, hardware, sensors? Or what are the foreseeable challenges for a novice in digital twin?
Yes, so the answer is all of the above. This is what's so exciting, but also so challenging about a digital twin, is that it really does bridge the physical and the virtual worlds. And so, of course, the hardware, the software, the algorithms, all of it has to come together. Where do you start? I think where you start is actually with a piece of paper and a pencil, and you really have to think about how to mathematically formulate the digital twin. What is the digital twin mathematically? And this is the gap that our work has been trying to fill, is to really lay that mathematical formulation for how to think about a digital twin in a generalized, abstract way that applies to many, many systems. And where we start is by defining the elements. So asking yourself, what's the state? What are the things about your physical system that you want to be able to track? For example, its structural health. Second, asking what data you have available to you, what observations you have, recognizing that your data will come to you in many different shapes and forms and on many different timescales, everything from the sensors on board your system that are giving you readings on a second-by-second basis, to the inspections that you might be performing on a weekly or a monthly basis. So characterizing your space of observations. Third, thinking about the control that you have over the system. What are the key decisions that you have to make, and how do they influence either the system itself, or perhaps how do they influence the data that you might be able to collect in the future? Fourth, thinking about how you measure success. What are your metrics of performance or reward? That might include successful operation, but of course also things like costs, perhaps also factor in risk. And then finally also thinking about other constraints, or we call them quantities of interest, that might be there in the system, things that you need to track and make sure you for example, satisfy certain constraints.
Very good. Karen, we really are looking forward to hearing your complete talk, which will take place at CAASE21, an online event on June 16th. Thank you very much for giving us a preview of your talk.
Thank you, Kenneth.
Until next time, this is Kenneth Wong for DE, and we are out.